Hello, my name is Luke Davison and I'm a Senior Research Assistant at Transformation Ireland, based in Trinity College Dublin. And today I am delighted to be presenting the data from a collaboration with one of the world's leading multinational pharmaceutical companies, Merck & Co. This work sought to investigate lipopolysaccharide administration by intraperitoneal injection and intracerebroventricular infusion as mouse models of neuroinflammation for the development of novel anti-inflammatory therapeutics for CNS disorders. Neuroinflammation is described as the activation of the brain's innate immune system in response to an inflammatory challenge and is characterized by a host of cellular and molecular changes in the brain. Chronic neuroinflammation, primarily mediated by microglial activation, has emerged as a key factor in the pathogenesis of a number of neurodegenerative and psychiatric conditions. As a result, there is an urgent need to develop anti-inflammatory therapeutics with novel mechanisms of action. Lipopolysaccharide, or LPS, is an outer membrane component of gram-negative bacteria that is commonly used to model neuroinflammation. Yet there is a paucity of studies comparing differences in peripheral and central inflammation in response to an LPS challenge. Here, we aim to directly compare the inflammatory response induced by LPS through intraperitoneal and intracerebroventricular administration in both the central and peripheral nervous systems in mice. We also aim to investigate the effect of subchronic and acute administration of the tetracycline antibiotic minocycline, as well as acute pretreatment with dexamethasone corticosteroid on intraperitoneal LPS-induced inflammation in mice. In terms of the methods, the study was broken up into 3 separate experiments. So for experiment 1, animals were administered either saline or one of 3 concentrations of LPS IP, 0.1, 0.25, or 0.5 milligrams per kilogram for 4 hours, with an N of 6 animals per group. For experiment 2, animals were administered either artificial cerebrospinal fluid or one of 3 concentrations of LPS i.c.v, 1 microgram, 5 microgram, or 20 microgram per mouse for 4 hours, with an N of 4 animals per group. 4 hours after LPS treatment in both experiments 1 and 2, animals were sacrificed with brain tissue and trunk blood for plasma isolation, collected for analysis of the levels of cytokines TNF-alpha, IL-6 and IL-1 beta, and chemokines CCL2, CCL3, and CCL4 using the Mesoscale Discovery platform. For experiment 3, minocycline was administered IP at 100 milligrams per kilogram, either for 2 days prior to LPS and a third time on day 3, 3 hours prior to LPS, or else just acutely 3 hours before LPS administration IP. Dexamethasone was administered orally 2 hours prior to LPS injection, before LPS was administered IP at 0.25 milligram per kilogram for 4 hours. Brain tissue and trunk blood plasma were collected and analyzed as in experiments 1 and 2, with N equals 10 animals per group. So results from experiment 1, LPS administered IP was found to increase the expression of all cytokines and chemokines analyzed in plasma. In brain tissue, LPS increased the expression of IL-6, IL-1 beta, and CCL2 in a dose-dependent manner. For experiment 2, LPS administered i.c.v increased the expression of all cytokines and chemokines in plasma, except for CCL2. In brain tissue, 20 micrograms of LPS produced an increase in the expression of all cytokines and chemokines analyzed. TNF-alpha and IL-1 beta were increased in brain tissue by 1 microgram and 5 microgram LPS. And finally, for experiment 3, dexamethasone but not minocycline reduced TNF-alpha, IL-6, IL-1 beta, and CCL4 expression in plasma and brain tissue following administration of 0.25 milligram per kilogram LPS IP. All data was analyzed via one-way ANOVA with Fisher's LSD post-hoc test. All values are expressed as protein concentration in picogram per mil, and data is presented as mean plus or minus standard error of the mean. So in conclusion, both IP and i.c.v LPS administration induced a robust peripheral and central inflammatory response, although the specific targets that increased in brain tissue differed between models. IP administration of LPS is sufficient, therefore, to induce a model of neuroinflammation responsive to anti-inflammatory drugs and shows advantages over the i.c.v model requiring surgical infusion. Neuroinflammation induced by i.c.v administration was also shown here to not be contained within the brain at the doses tested. And finally, in terms of funding, this research was funded by Transformation Limited, and MSD, London, UK, and Merck Sharp and Dohme Corp. I would just like to thank all of my colleagues and our collaborators at Merck for all of their help and expertise over the duration of the study. I look forward to fielding any questions that you may have, and many thanks for listening.